What causes underfitting? Underfitting happens when a model doesn't fit well, neither the training data nor new unseen data. On the right, we have plot curves of our measured training and test set errors. If we have underfit our data, it might be because we need to train the algorithm for longer. Problems of underfitting are also called high bias problems. Bias in a model is reduced as the complexity of the model increases. A model's complexity is related to its capacity to learn. Too low and we'll likely underfit our data. Too high and we'll likely overfit. Remedies for underfitting, therefore, may be to train for longer, to try adding more features, or to try a different model entirely. Adding more data doesn't usually help with underfitting. Overfitting is when our model fits too well to the training data. It has found superfluous details and noise within our training examples, and has used these in reducing its training error. Unfortunately, this means it will rely upon these when it comes to predicting based on new, unseen data. Overfitting is much more common with larger model capacity, and so tends to be more of a problem with deep networks than with shallower machine learning algorithms. Problems of overfitting are also called high variance problems. I like this particular quote from John von Neumann, the early computer pioneer. I think it captures the notion that we should always be careful of model complexity and overfitting our data. We can also overfit from overtraining. During training, usually our training error and generalization error decrease initially. However, if we train for too long, we may end up forcing the algorithm to try to fit closer to its training data, and this can end up sacrificing the generalizability of the solution. Regularization is the term used for any modification to a learning algorithm to reduce its generalization error. Overfitting decreases with more diversity in the training set, and so remedies for overfitting can include adding more varied training data, stopping training early, and other techniques to artificially limit the detail our model can capture, such as random weight dropout, sharing of weight parameters, or even using a smaller and less complex network. In contrast, training for longer, adding more features, or choosing a more complex model will often exacerbate a problem of overfitting. Hyperparameters are variables encoding design choices that control and modify the operation of our learning algorithms. These parameters are not themselves optimized during the training process, and are most often codified design choices made by hand. To evaluate the effects of these hyperparameters, we need an additional dataset. This is called a validation set or a cross-validation set. It helps us validate our model design choices. So, we design a model, use our training set to train it, and use our validation set to verify the choices we made in this model design. If we change our model, we repeat. Once we're happy with the model, we then use our test set to verify the model's generalizability. Why do we use a separate test and validation set? Because the validation set is used to select the final model. Therefore, we cannot accurately estimate the performance of the model on unseen data unless we reserve a test set. A typical split for your labeled dataset might be roughly 60% for training, 20% for validation, and 20% for test. But something like 70%, 15%, and 15% would work just fine too. In conclusion, the more varied and representative your training data, the less problems you'll probably have with overfitting. Overfitting is more common with deep networks than with shallower machine learning algorithms, as deeper networks have greater model complexity. It is therefore important to select an appropriate model for the data complexity you're trying to learn. Sometimes a simpler learning algorithm, like a support vector machine, can work very well for a classification problem. Where you are trying to automatically learn feature extractors and other complex behaviors, then a deeper model is much more appropriate. To detect problems of overfitting, watch for low training error, but increasing test error during training. If you are overfitting, consider adding more varied training examples. Consider stopping training before your test error increases again, and consider investigating regularization techniques for your model. So in this lesson, we looked at the topic of deep learning and how it all works. We will continue our journey into deep learning algorithms by specifically looking at the basic building blocks for convolutional neural networks.